Today we're going to be looking at some more examples of solving application problems with exponential and logarithmic functions. So a couple different examples than what we looked at on Friday. Up at the top, you'll see that there's some helpful steps for solving application problems. Basically, we're going to read the problem, underline some important pieces of information, look for what we need to substitute in, and then actually solve the equation. Let's start with example one. A couple invests $8,000 in a bond fund. The interest rate is 4.5% compounded monthly. Keyword. Determine how long it will take for the initial investment to double. So when we're talking monthly compounding, we're talking about the equation A is equal to P times 1 plus R over N to the NT power. And we basically need to figure out, well, what do we have? What do we need? So A, you're talking about P, we need an R, and we need an N, and we need a T. So we're investing $8,000. That's what we're starting with. So that's our P. Interest rate is 4.5%. So I'm going to convert that to decimal, so 0.045. Compounded monthly means that we're compounding 12 times, which is our N. We want to determine how long, so our T is what we're looking for, and we're doubling our initial investment, which means that we're taking this 8,000 and we're multiplying it by 2. That'll give us 16,000. So when we go to plug in this information into our formula here, that's going to tell us that we're going to have 16,000 equal to 8,000 times 1 plus the 0.045 divided by 12 raised to the 12t power. And that's going to be the variable that we're solving for is in the exponent. So we have to basically use our order of operations to like undo this stuff and combine like terms. So I'm going to start with the inside of the parentheses here. So 16,000 is going to be equal to 8,000 times 1 plus. I'm going to go ahead and divide that 0.045 by 12. That'll give me 0.00375 raised to the 12t. I'm going to combine those in there. So 16,000 is equal to 8,000 times 1.00375 raised to the 12t power. Here's my base. I need to get this by itself, so I have to undo that 8,000. I'm going to go ahead and divide that on both sides. So divide that by 8,000, divide the other side by 8,000. That's going to leave me with just a 2 over here equal to 1.00375 raised to the 12t. So basically what I need to do is I need to get that exponent down. So I have to undo that base of 1.00375, which means that I'm going to take the log base 1.00375 on both sides. So what this is going to look like is I'm going to have log base 1.00375 of the left-hand side, which is 2, equal to, over here on the right-hand side, log base 1.00375, whoops, of 1.00375 raised to the 12t power. And here's our inverse property that's going on here. This is just 1. Log base 1.00375 of 1.00375 is just 1. So that's going to leave us with just log base 1.00375 of 2 over here. That's going to bring down our exponent of 12t over here. So I need to use a change of base here. That's going to tell me I'm going to do log of 2 divided by log of 1.00375. That's going to be equal to 12t. I'm going to go ahead and use my calculator to calculate that, which is about 185.186 equal to 12t. And then all I have to do here is divide by 12 on either side. Divided by 12, divided by 12. That's going to tell me that my t, or my time, is about 15.4, and my units here are years. All right, so let's look at another example. So example 2, the retail sales Y in billions of an e-commerce company in the United States from 2002 to 2020 can be modeled by this function here. So we're noticing that we have an ln here, so different type of function than what we were working with in the first example. It's telling us T is representing the year since 2002. We want to know during which year did the sales reach 108 billion. So here we already have the function. We basically are left with 2 variables, a Y and a T. So it's telling us that the retail sales is the Y, and we know that T represents time. So if I'm looking for during which year, that means that I'm solving for T. So that means that this 108 billion is actually my Y value. So I'm going to go ahead and plug that in. So 108 is equal to negative 549 plus 236.7 ln of T. And this is the variable that I'm solving for here. So basically, I have to undo all this stuff that's going on around the ln of T. So first thing we're going to go ahead and do is add 549 to both sides. That's going to give me 657 equal to 236.7 ln of T. And then I want to get this ln by itself, so I want to undo that 236.7 by division. So when I divide 657 by 236.7, that's going to leave me with about 2.776. And that's equal to ln of T. So I have to undo this ln, but remember that on an ln, the base here is really E. And that means that when I want to undo an ln equation, I want to go ahead and make this into exponential form. So my base here is E. So I'm going to take the E. I'm going to raise it to the exponent of 2.776. And that's equal to T. And again, I'm undoing the ln by using the base of E. So when I write this next step, I'm not rewriting the ln. The E is undoing it. So in my calculator, I just have to evaluate what is E raised to the 2.776. That's approximately 16.1. But that's not what the question is asking. It's asking during which year, which is where we need to use this T is representing the year since 2002. So if I'm saying that my T is starting in 2002 and I'm going 16.1 years later, that means that 2002 plus 16 years leaves me with the year 2018. So I'm going to say the sales reached 108 billion in 2018. So to fully answer that question, to write myself a little sentence here, the sales reached 108 billion in the year 2018. And you'll notice that the next example looks pretty similar. It's kind of asking for the same information, but our equation again is going to be a little bit different. So the population P of a certain city is growing according to this model. P is equal to 10,000 log base 5 of T plus 5. So now we're dealing with a log base 5, where T is the time in years. If T equals 0 corresponds to the year 2000, in what year does the population reach 20,000? So again, it's asking us in what year. So our answer is going to look pretty similar to the last example. So here we are left with two variables, a P and a T. So it's asking me in which year. That means, again, we're solving for T. So that means that our P, or our population, is 20,000. So I'm going to go ahead and in that equation plug in 20,000 on the left-hand side. So 20,000 is equal to 10,000 times log base 5 of T plus 5. And I need to solve for the T here. So I need to get this log base 5 by itself. So I'm going to go ahead and undo that 10,000. So I'm going to go ahead and divide that out. So that's going to leave me with just a 2 over here. So 2 is equal to log base 5 of T plus 5. And now that I have this log base 5 by itself, I'm going to do something pretty similar to what I did in the last example, except now my base isn't E, my base is 5, but I'm still going to rewrite this in exponential form. So the base here is 5. I'm going to raise it to its exponent of 2. And I'm going to set it equal to that T plus 5. Again, when you're rewriting this in exponential form, you're undoing the log. So in this step, you don't need to rewrite the log. You're undoing it by doing this exponential form. So I'm going to go ahead and simplify this. Well, on my left-hand side, 5 squared is just 25, equal to T plus 5. And I just have to solve for T here. So subtract 5 on both sides. That's going to leave me with a T equal to 20 years. But again, it's asking me in what year. So if T is equal to 0 is corresponding to 2000, I'm saying that this is happening 20 years later. So 2000 plus 20 years is in the year 2020. So I'm going to say the population reached 20,000 in the year 2020. And that would answer my question completely. Now it's your turn to try some practice problems. Let me know if you have any questions.